All right, picture this. You're literally strapped into a missile, rocketing down a stretch of asphalt at over 340 kilometers per hour. A tight corner is coming up incredibly fast. Now, in your normal everyday road car, you'd be bracing for a serious impact. But in a Formula One car, you're about to kick off one of the most violent, technologically insane, and microsecond precise events in all of sports. Welcome to This Explainer. Today, we're diving deep into the absolute engineering marvel that is Formula One braking. We're going to break down exactly how these machines harness massive physical forces and some seriously cutting-edge software to bring a car from mind-bending speeds down to a crawl in literally just seconds. To really wrap our heads around this, we have to start with the sheer, brute physical violence of the deceleration. When a driver stomps on the brakes at the end of a long straight, they aren't just slowing down, they are violently shedding speed from roughly 340 kilometers per hour down to 80 in under 150 meters. I mean, that entire process takes barely 2 to 4 seconds. And this is only physically possible because immense aerodynamic downforce is basically gluing the car to the track. The end result? The driver gets hit with a brutal 6G of deceleration force. That means they are thrown forward into their belts with 6 times their own body weight. Honestly, it's enough force that a normal person wouldn't even be able to keep their head upright. So that brings us to the core mystery we are solving today. How on earth do you engineer a vehicle to survive those kinds of 6G forces while generating friction temperatures that rival molten lava at 1200 degrees Celsius? And get this, doing it all without the safety net of the anti-lock braking systems we all take for granted on our daily commutes. To figure this out, we're going to trace the exact sequential path of the braking action. We'll start right from the immense pressure of the driver's foot, travel through the crazy complex hydraulics, and end right at the contact patch where the rubber meets the road. Okay, so it all kicks off in the cockpit with a physical effort that is just staggering. In the absolute heaviest braking zones, the driver actually has to put up to 160 kilograms of operating force into the brake pedal. Just think about that for a second. That is the equivalent of leg pressing a full-size refrigerator with one leg, repeatedly over a 2-hour race. To even handle this without snapping, the brake pedal is a bespoke piece of carbon fiber, molded exactly to that specific driver's foot. It's even covered in heavy-duty grip tape so their heel doesn't slip when the pressure is on. Now, that massive 160-kilogram push compresses what's called a dual-circuit tandem master brake cylinder, and the contrast here between your daily driver and an F1 machine is wild. Your standard road car, it relies on heavy steel brake discs that weigh around 25 kilograms each. But an F1 car, it's all hyper-light carbon components. A single F1 brake disc weighs a mere 1.6 kilograms. Even the calipers, which are machined from this super exotic nickel-plated aluminum lithium alloy, weigh less than half of a standard sports car caliber. Every single gram on this setup is totally optimized. So at the front of the car, that dual-circuit system takes over. The tandem master cylinder takes that massive pedal force and splits it. Up front, it's actually beautifully pure and mechanical. It delivers raw, unassisted hydraulic fluid pressure straight to those massive front calipers. There's zero computer intervention happening here. The fluid just violently rushes in, pushing 6 pistons outward, which then ruthlessly clamp the carbon brake pads against the carbon disc. It's just raw, old-school mechanical friction doing the work. But as you know, pure friction creates an unbelievable byproduct: heat. The friction generated by slowing the car down so aggressively spikes the temperature of these carbon discs to over 1200 degrees Celsius. That's exactly why, especially if you're watching a night race, you literally see the brake discs glowing this incredibly bright cherry red. To stop the entire assembly from just melting into a puddle, engineers physically machine all these intricate ventilation slots and drillings directly into the disc to vent that trapped heat out. And the material science required to actually survive this? Mind-blowing. These discs are made of reinforced carbon-carbon. This is literally a composite material that was originally developed for the nose cones of intercontinental ballistic missiles in the space shuttle. To manage that 1200-degree heat inside the modern 18-inch wheels, engineers drill up to 1,500 microscopic computer-perfected cooling holes into each disc. It exponentially increases the surface area for airflow. At $10,000 a pair, they are absolute masterpieces of engineering. Plus, they aren't even solidly bolted to the wheel. They're mounted on these floating splines. This intentional float lets the disc expand under the massive heat and absorb crazy curb vibrations without shattering. But here is the truly terrifying catch with all this heat management. You absolutely need the brakes hot enough to bite. But if you overcool them, you are courting disaster. As industry experts will tell you, if a car is screaming down a long straightaway, the massive airflow blasting through the brake ducts can drop the brake's temperature by up to 1,000 degrees. If a driver suddenly hits the brakes when that carbon is too cold, the violent instant spike in temperature causes what's called thermal shock. The disc can literally explode right inside the wheel. It is an insanely razor-thin margin between peak cornering performance and total failure. All right, so we've covered the pure mechanical front brakes. Let's move to the rear of the car, because this is where Formula One essentially turns into a fighter jet. Unlike the front, when the driver stomps on that 16-kilogram pedal, the pressure going to the rear isn't actually a direct command to the calipers. Nope, it's only a request. A sensor reads exactly how hard the driver is pushing, and an electronic control unit, a computer, actually steps in to decide how to stop those rear wheels. We call this system brake-by-wire, and it is absolutely vital. Why? Because the rear of the car is actually being slowed down by 3 entirely different forces that have to be blended perfectly in a fraction of a millisecond. First, you've got the traditional carbon pads and discs. Second, you have engine braking, the natural drag of the internal combustion engine when you lift off the gas. And third, and most crucially, you have the MGUK. This is the hybrid electrical motor which instantly flips into a generator under braking to harvest energy from the rear wheels. The computer acts as an active restrictor, rapidly adjusting the hydraulic fluid to make sure these 3 forces always add up to the exact stopping power the driver asked for. Now here's why this brake-by-wire system has become the ultimate performance game-changer, especially as we look ahead to the 2026 engine regulations. The rules are shifting a massive amount of power over to the electrical side. The MGUK hybrid motor's output is jumping from 120 kilowatts to a staggering 350 kilowatts. It's going to be harvesting 8.5 megajoules of energy per lap, up from just 2. Because pulling that much energy creates an unbelievable amount of drag on the rear wheels, the hybrid motor is now doing the vast majority of the rear braking. The ECU has to perfectly restrict the hydraulic brakes so seamlessly that the driver doesn't even notice the hybrid motor is doing all the heavy lifting. If that blend is even a little bit clunky, the driver loses all confidence in the car. And because software is running the show back there, it unlocks this incredibly powerful tool for the driver called brake migration. Since the ECU controls the rear brakes, engineers can actually program the car to dynamically change the front to rear brake bias while the driver is in the middle of a corner. So at a high-speed track like Monza, you'd want a static, front-heavy profile so the car doesn't get twitchy and spin under 6G deceleration. But at a tight, twisty street circuit like Monaco, the software uses aggressive rear migration. As the driver turns the steering wheel, the computer secretly shifts the braking force to the rear tires, freeing up the fronts and actively helping the car pivot around the hairpin. The driver doesn't even move their foot. The computer just magically helps the car turn. But let's ground ourselves for a second, because all of this digital magic happens entirely without the safety net of an anti-lock braking system. These drivers are operating right on the ragged, razor-sharp edge of adhesion. At 340 kph, they rely entirely on that massive aerodynamic downforce to push the tires into the track so they can hit the brakes that hard. But as the car physically slows down, that downforce bleeds away. If the driver doesn't perfectly ease off the pedal, or if that brake migration software gets the balance even a tiny bit wrong, the rear tires will lock up instantly. A locked tire will scrape off its hot rubber, creating a massive flat spot that will vibrate the car to pieces, or worse, the rear end just steps out and sends the car spinning straight into the barriers. It all boils down to this incredible, high-stakes interplay between raw human bravery and absolute digital precision, which leaves us with this final thought to chew on. We've talked about the 160 kilos of leg force, the aerospace-grade carbon glowing at 1200 degrees, and the algorithms perfectly balancing the hybrid motor with the brake pads. But at the end of the day, it requires a human being to barrel toward a concrete wall at over 300 kilometers per hour, mash their foot into a piece of carbon fiber, and just trust, with absolute certainty, that the computer will interpret it perfectly and stop this missile on a dime. It's a breathtaking feat of engineering and a real testament to the absolute limits of human performance. Thanks so much for joining me on this explainer, and next race, definitely keep your eyes on those braking zones.